In this video, we're going to talk about VSEPR theory and what it has to do with molecular geometry. Perhaps you've seen this word in your textbook. It stands for valence shell electron pair repulsion. And the basic idea is that we can predict the shape of the molecule based on the fact that electrons repel each other. So electrons, they want to be as far apart as possible. So with that idea in mind, we can predict the shapes of certain molecules. Now, the first type of geometry that you need to be familiar with is the linear molecular geometry. And molecules that have this type of shape, for example, are BeCl2, which looks like this. This is beryllium chloride. As you can see, it looks like one straight line. And the angle of a straight line is 180 degrees. So that's the bond angle of a molecule with a linear geometry. Now there's some other examples. For example, carbon dioxide is another molecule with a linear geometry. It looks like this. It looks like one straight line. So any molecule where you have an atom at the center and two other atoms on the sides is a linear molecule. This is the generic structure of a linear molecule. Now this is another example of a linear molecule, and it's quite different from the first two. This is the triiodide ion, and this little structure looks like this. You have three atoms. The whole thing is an ion. Now, the middle one has 3 lone pairs, and the other two also has 3. But the geometry, it's straight. It's a linear molecular geometry. Now, the next type of molecular geometry that you need to know is the trigonal planar structure. When you hear the word tri, what do you think of? Tri represents 3, and planar means it's flat as a paper. A good example of this structure is BH3. So you have boron at the center, and the 3 hydrogen atoms are going to be spaced as far apart as possible. So it looks like this. Now, a full circle represents an angle of 360 degrees, and if you divide that by 3, you can get the bond angle between hydrogen atoms. And so the bond angle for a trigonal planar structure is 120, which is 360 divided by 3. Some other examples of a trigonal planar structure is COCl2. So in this structure, carbon has a double bond to an oxygen, and it's attached to 2 chlorine atoms. So anytime you have an atom at the center, surrounded by 3 things, and if the central atom doesn't have any lone pairs, then what you have is a trigonal planar structure with a bond angle of approximately 120. Now the next structure that we need to talk about is the tetrahedral molecular structure. So when you hear the prefix tetra, what do you think of? Tetra is equivalent to 4. So therefore, in this structure, we're going to have an atom surrounded by 4 other atoms. And that's the tetrahedral structure with a bond angle of about 109.5. So methane fits this example. So in methane, we have carbon in the middle surrounded by 4 hydrogen atoms. Now this is not a 2-dimensional structure, it's a 3-dimensional structure. Because if you take 360 divided by 4, you get 90. And it's not 90, it's actually 109.5, based on the way these atoms arrange themselves in 3-dimensional space. Another example of a tetrahedral structure is silicon tetrafluoride. Like carbon, silicon is surrounded by 4 atoms. In this case, 4 fluorine atoms instead of 4 hydrogen atoms. But the structure, the geometry, is very similar. You just have different atoms. The bond angle is still approximately 109.5. Now, the next structure that you need to know if you have a test coming up is the trigonal pyramidal structure. Once again, we hear the prefix tri, so there has to be 3 of something. Now, this is different from the trigonal planar structure. The trigonal pyramidal structure has an atom at the center with a lone pair. Now, that atom is still surrounded by 3 other atoms. So it looks like this. That's the trigonal pyramidal structure. Now, just to compare it with the trigonal planar structure, I'm just going to draw this right next to it so you can see the difference. The trigonal planar structure doesn't have any lone pairs on the central atom. It's simply surrounded by 3 other atoms. The trigonal pyramidal structure has 3 atoms attached to the central atom plus a lone pair, so it has 4 things. A good example of the trigonal pyramidal structure is NH3, ammonia. In this structure, nitrogen has 1 lone pair and it's attached to 3 hydrogen atoms. Another example is pH3. So if you notice something, I just want to point something out. Elements that have the trigonal planar structure tend to be in group 5, like NH3, pH3, and ASH3, when hydrogen is like the only other atom attached to it. And the ones that have a trigonal planar structure tend to be in group 3, but not always though. So BH3 is an example. Another example includes AlCl3. So these elements are in group 3A, and these elements tend to be in group 5A. So that's another quick way to identify which one is going to be trigonal planar, which one's going to be trigonal pyramidal, if there's no double bonds involved. Because we did have the example where it was like COCl2, but the carbon attached to an oxygen had a double bond. If there are no double bonds, for the most part, these elements will be in group 3A, and these will be in group 5A. At least that's just a pattern I've seen. Now, going back to the trigonal pyramidal structure, there's one other thing I need to mention, and that is the bond angle. I'm going to use ammonia as an example. So the bond angle for ammonia, make sure you know this because it's a common test question, it's about 107 degrees. And so that's it for the trigonal pyramidal structure. Just want to mention that before I forgot it. Now, the next geometry you need to be familiar with is a bent molecular geometry. And a good example for this one is water. Water has a bent shape. Oxygen contains 2 lone pairs, and those 2 lone pairs causes the hydrogens to be in a bent structure. Now perhaps you've seen water drawn like this, and this is a common mistake, so you don't want to do it. But rather, the lone pairs causes the hydrogens to be bent with respect to each other. And the bond angle for water is 104.5 degrees. Another example of a bent structure is the sulfur dioxide molecule. In this structure, sulfur has 2 oxygen atoms. One has a double bond and the other has a single bond. And sulfur also has a lone pair. It doesn't have 2 lone pairs in the case of oxygen, but it has 1 lone pair. And the bond angle is less than 120. Notice that this is similar to a trigonal planar structure in the sense that it has 2 atoms and a lone pair. a trigonal planar structure has 3 lone pairs with a bond angle of about 120. So SO2 has 3 things, 2 atoms and a lone pair on the sulfur atom. And that's why the bond angle is similar to a trigonal planar structure. Water is somewhat similar to a tetrahedral structure. In the tetrahedral structure, there's 4 things or 4 atoms attached to the central atom. In the case of oxygen, it has 4 things, 2 atoms and 2 lone pairs. That's why the bond angle is close to that of a tetrahedral structure, which is supposed to be 109.5, but in the case of water, it's actually 104.5. Now, I want to put certain molecules together. So, for a tetrahedral structure, in the case of methane, it has 4 groups, 4 atoms attached to it. The bond angle is 109.5. Now, if we replace one of those atoms with a lone pair, as in the case of ammonia, we're going to get the trigonal pyramidal structure. And because we still have 4 things, in this case 3 atoms and a lone pair, the angle is going to be close to 109.5, but it's a little bit less. If you subtract this by 2.5, you're going to get 107 degrees. And that's the bond angle of ammonia with its trigonal pyramidal molecular structure. The next one is water, which looks like this. It has 2 lone pairs instead of 1, but it still has 4 electron groups, 2, 3, 4. So the bond angle for this is 104.5 degrees. But the molecular structure is bent. And we said this is tetrahedral, and ammonia is trigonal pyramidal. Now let's draw the trigonal planar structure. Let's use BH3 as an example. So boron is attached to 3 atoms, so therefore the bond angle is 120 degrees. Now similar to BH3, we have SO2. So one of the atoms in this structure is replaced with a lone pair. So sulfur dioxide is attached to, the center atom is attached to 2 atoms and a lone pair. So you still have 3 things around it, which means the bond angle is close to 120. But it's not exactly 120, so it's really a little bit less than 120, but it's close to it though.